And then once it actually hits the Earth, then we can get the readings on it, and the readings were really quite spectacular. Some big numbers coming in, and everybody that's looking up outside, especially in the northern half of the country, can see this. I've seen some pictures and videos coming in out of Texas, Oklahoma. Aurora is visible there. Massachusetts, Maryland, South Dakota, Nebraska, Kansas. I'm just naming off the top of my head where I've seen some of these pictures. So a G4 storm, which is severe.
Something massive is coming from the sun. A colossal G4 geomagnetic storm, one of the most powerful in years, is now barreling toward Earth, carrying with it a surge of magnetic energy that could shake our planet's magnetic field itself. The sun has just unleashed a wave of magnetic fury unlike anything we've seen in a long time. Billions of tons of charged particles are racing toward us at incredible speeds, a river of plasma traveling through the void. From observatories to satellite control rooms, scientists are watching in awe. Space weather monitors are lighting up with alerts, their screens flashing red as readings surge past normal thresholds. This isn't just another solar flare, it's a planetary-scale event. For 3 days straight, the sun has been erupting, each outburst fiercer than the last. The first blast came like a warning, a bright pulse of light captured by NASA's solar observatories. Then another followed, and then a third, faster and stronger, caught up to the first two, fusing their magnetic fields into one expanding storm front. These waves of plasma, called coronal mass ejections, or CMEs, are the true giants of solar activity. They hurl magnetized gas into space with unimaginable force, enough to compress Earth's magnetic shield when they arrive. On the models run by NOAA's Space Weather Prediction Center, Earth appears as a tiny green dot, dwarfed by great arcs of color. Those ribbons show the storm's density and velocity, its strength swelling as it nears. The first eruption struck on Tuesday night, with the second expected to arrive by Wednesday morning, and the third sweeping through by evening. Scientists rarely see solar activity like this, 3 flares in such rapid succession, each more powerful than the last. It's an extraordinary chain reaction, one researcher noted, a solar machine firing on all cylinders. But how bad could it get? To answer that, we have to look back in time. In 1859, something similar, though far greater, swept across our world. Astronomers of the era, limited to simple telescopes and hand-drawn sketches, could not have known what was about to unfold. Among them was Richard Carrington, a British astronomer and pioneer in solar observation. On the morning of September 1st, as Carrington traced the outlines of a massive sunspot group, he witnessed something no human had ever recorded before. 2 brilliant flashes of white light bursting from the solar surface. This was the first documented observation of a solar flare, a visible manifestation of an immense release of magnetic energy from the sun's atmosphere. Less than a day later, Earth was engulfed in the most powerful geomagnetic storm ever observed. A massive coronal mass ejection, or CME, an immense cloud of magnetized plasma ejected from the sun, had raced through the 150 million kilometers of space between the sun and Earth in an astonishingly short time, about 17 hours. Typical CMEs take 2 to 3 days to reach Earth. The unprecedented speed of this one indicated it was traveling at over 2,000 kilometers per second, driven by a shock wave of immense energy. When the solar plasma struck Earth's magnetosphere, the effects were immediate and dramatic. The planet's magnetic field wavered violently, triggering electrical currents across the atmosphere and the ground. Around the world, people looked up to find the night sky ablaze with color. Auroras painted the heavens in shades of crimson, green, and violet, not just at the poles, but across much of the globe. Reports from the time describe auroras visible as far south as the Caribbean, Central America, southern Japan, and even Queensland, Australia. In the northeastern United States, witnesses said the light was bright enough to read newspapers at midnight. But the spectacle came with chaos. The 1859 storm struck during the early years of telegraphy, the first global electrical network, and the effects on that fragile system were extraordinary. Telegraph lines across Europe and North America began to spark and fail, Operators experienced electric shocks when they touched their instruments. Papers burst into flame. At some stations, even after batteries were disconnected, telegraph systems continued to transmit messages powered solely by the geomagnetically induced currents flowing through the wires and the Earth itself. The planet's magnetic field had, quite literally, become the power source. Magnetometers at observatories around the world recorded violent fluctuations in Earth's magnetic field. The readings were so extreme that the instruments were driven off scale. Scientists later determined that the event represented the strongest geomagnetic disturbance in at least 500 years. It was, and remains, the most powerful solar storm ever recorded in human history. The phenomenon was later named the Carrington event, in honor of Richard Carrington's discovery. His observation provided the first concrete evidence linking solar activity with disturbances on Earth, marking the birth of modern space weather science. Subsequent analyses suggest that the flare Carrington saw may have been an X-45 class event or stronger, several times greater than the most powerful flares detected in the space age. Modern studies have reconstructed the event in detail, using historical records, magnetometer data, and ice core samples, which preserve traces of high-energy particles that bombarded Earth's atmosphere. These analyses confirm that the Carrington event was caused by a sequence of solar eruptions that preconditioned the solar wind, clearing the way for the final CME to reach Earth unusually quickly and with exceptional intensity. The result was a perfect alignment of speed, magnetic orientation, and plasma density, a combination that maximized the energy transferred into Earth's magnetosphere. The 1859 storm was extraordinary not only for its beauty and scientific significance, but also for its implications. It struck a world that was, electrically speaking, still in its infancy. There were no satellites, no power grids, no radio communication, and yet the effects were still devastating for the limited technology that existed. Telegraph networks, the backbone of 19th century communication, were crippled for hours.
Now, imagine that same force unleashed on our world today. Satellites that control communications, weather tracking, and navigation all could be thrown into chaos. Airplanes could lose radio contact as signals distort and fade. Transformers could overload under sudden electrical surges, potentially triggering power outages on continental scales. The invisible waves of magnetism that make the aurora shimmer could, in an instant, become a threat to the infrastructure that defines modern life. And today, history might be repeating itself. The sun's unleashed an enormous G4-class geomagnetic storm, powerful enough to disturb satellites, disrupt communications, and create dazzling auroras far beyond the poles. This isn't a minor flare or pretty display in the northern sky. It's a magnetic blast with the strength to shake Earth's protective field. 3 solar eruptions are converging, their combined impact expected to pulse through the magnetosphere over several days. Signs of disturbance may soon appear. Spacecraft orbiting Earth might switch into safe mode to protect their electronics. Airlines could begin watching radar interference closely, possibly rerouting some high-latitude flights to avoid radio blackouts. GPS systems may experience temporary inaccuracies, and power companies across the northern hemisphere might go on alert for geomagnetically induced currents that could overload transformers. Even now, invisible torrents of plasma could be nearing our planet's magnetic bubble, ready to compress it, twist it, and send ripples and energy toward the poles. But in the midst of the danger could come beauty. Across northern skies, auroras may soon glow over regions that rarely see them. Streaks of pink and green above Minnesota, red waves that might dance over Scotland, faint blue arcs possibly glimpsed from Canada's prairies. The atmosphere could come alive, molecules of oxygen and nitrogen colliding with particles from the sun, releasing light as a natural symphony of color. It's one of those moments when science and wonder might meet in the same sky. In the data, scientists track this spectacle with a set of critical parameters. The BT, or total magnetic field strength, measures the storm's overall force. The BZ, its north-south magnetic orientation, determines whether Earth's field can absorb or resist the incoming energy. When that BZ turns negative, the two fields link like keys fitting into locks, allowing the solar wind to pour directly into Earth's magnetosphere. That's when things get dramatic. Auroras surge southward, power systems strain, and the storm truly begins. Right now, the BZ values are fluctuating wildly, dipping below -20 at times, the threshold for mid-latitude auroras. For observers in the northern United States, this means the lights could descend far beyond the Arctic Circle, visible from states like Iowa, Nebraska, and Michigan. For those farther south, a faint red shimmer on the horizon might be their only clue to the storm raging above. NOAA's KP index, the global scale for geomagnetic activity, is projected to hit 8, possibly 9, during the peak of this event. That's a level reached only during the most severe solar storms. The hours between 11 p.m. and 3 a.m. are expected to offer the best chance for viewing, provided clouds don't block the display. Forecast models show the clearest skies stretching across the Dakotas, Minnesota, Wisconsin, and parts of Montana. Perfect vantage points to witness the spectacle. Elsewhere, thin cirrus clouds may scatter the light, but not hide it completely. Even under less ideal conditions, the storm's brightness could still pierce the haze, painting the heavens with slow-moving fire. Yet as stunning as it is, the sight carries an uneasy undertone. Behind every ripple of color lies a tremendous exchange of energy, solar wind slamming into Earth's magnetic armor, compressing and distorting it. For most of us, it's invisible, but for those who monitor the magnetosphere, it's a battle of forces measured in microteslas and megawatts. The magnetometers at research stations pulse with readings that trace the storm's impact, a heartbeat of the planet itself reacting to the sun's assault. For scientists, this storm is both a challenge and an opportunity. Each CME that strikes Earth offers a rare window into how our planet responds to solar aggression. The data they collect now will refine future forecasts, helping humanity prepare for the next great flare, because one day it could be far worse. The Carrington event was not unique, it was simply the strongest on record. Statistically, storms with that magnitude are expected every century or two. The last major one in 1989 plunged parts of Quebec into darkness for hours. If another true Carrington-level blast occurred today, it could bring down entire grids and satellites in minutes.
And so, as this G4 storm surges, the world watches both with excitement and caution. Power grid operators adjust voltages and reroute current to avoid overloads. Astronomers compare real-time readings from satellites and ground-based sensors. Commercial pilots glance at magnetic storm alerts as they cross the upper latitudes. Astronauts aboard the International Space Station are briefed on increased radiation levels. Space weather, once an obscure field, is now a vital branch of planetary defense. But beyond the charts and alerts, there's a deeper sense of awe, a reminder of how small and vulnerable our planet really is. We live on a world protected by a thin magnetic shell, a shield that deflects the sun's fury every day. Without it, the atmosphere would erode, the oceans might boil away, and life as we know it would vanish. Yet that same shield is fragile, quivering and groaning under the weight of cosmic storms. Every aurora we see is the visible trace of that defense in action, a brilliant scar of light on the edge of a vast invisible struggle. As the storm unfolds, it becomes clear that we are not just passive spectators. We are participants in an ongoing dialogue between Earth and its star, a conversation written in magnetism and plasma, in light and darkness. The sun gives us warmth and sustains every living thing, but it also reminds us from time to time of its power. It's moments like this that remind us we live on a tiny world orbiting a volatile star. For all our technology and progress, we remain tethered to the moods of the sun. A single eruption can ripple through space, touching everything we've built, from the satellites above to the power lines below. The storm now sweeping toward us is both a warning and a wonder, proof that we are, despite all our knowledge, still at the mercy of forces far beyond our control.